Alex keeps swearing.
Ah,
H2O,
Raheem,
H2O, H2O.
why aren't you at home? Why are you at home, Raheem?
Well, it's a funny situation in Trinity.
Funny.
It's just that
Uh-oh. I have a bad feeling about this.
no, it's like today's like a big review day, so
I see. Today's a big review day. Why is this happening?
Eric, why are you all the way over there?
Hi there. Is that Akshay? I think that's Akshay. How are you?
I'm good. How are you?
I'm okay. And then we have Samia and Sam. How was chapel on?
Actually, Raheem are skipping today, so.
Oh Lord.
Never mind, Eric.
Okay. Here we are. Okay. And you're dressed very goth today, Sam.
What's that?
You're dressed very goth today. Are you going to go to your emo band later?
Yeah.
I so see it.
Yeah, but
I'm not surprised.
this is my science life, science mathematics.
You know who is a closet? You know who's a closet goth, Sam? Closet goth, Max Allen.
Yeah.
Max Allen is a closet goth. So you and he can read your Twilight fan fiction together.
No, I think Jasper's goth and he's overcompensating by wearing.
No, that's another. You can close the door, Eric.
So I'm a closet guy.
I'm trying to. My thing is not.
Oh my God! This story of my math life.
This is straight of your math life, really.
Do you have a math life?
I know. I love that you have a math life. Why is this here? I don't know. Okay. This is our last. Hey there. Who we got? Who's that? Who's that? Is that Alex Powell?
Jack, why are you sitting like one seat?
Why aren't you at school, Alex Powell?
He doesn't like you.
I'm so bad at it now.
I've got various
Oh my God.
outside of school things that I needed to finish today.
I see how it is. He's sick.
Outside of school.
Sick. Okay, well that's good.
Eric,
I mean, it's not good that you're sick, of course, but still, we're pleased to see you today. So I gave you a wonderful Christmas card here. I actually read a book recently that I think you'd all enjoy called Zombies in Calculus. Have you heard of this book?
No.
Oh, well, it is a highly well, actually, there are too many zombies in the book, but it is called Zombies in Calculus. It's heavy on the zombie, light on the calculus. But it really is a book about differential equations written by some Williams professor. Can you imagine? Okay, anyway, here we go. Here's where we're going to start today. So let's do this problem to begin and get our day started right. I don't know why this is not displaying, so I apologize. Input. Yeah. Okay, that's good. I don't know how I stop this.
Oh. It's not good.
We have a beautiful view of Alex Powell's tree outside of his window. Maybe bamboo. Alex Powell, we have an amazing view of the bamboo outside your window. Is that bamboo?
Oh no, that is a palm tree.
A palm tree? What are palm trees? I've never heard of a palm tree.
Yes, I have.
Don't they die
Akshay
in
and
the winter?
Raheem, why aren't you at school?
They have things to do.
Yeah, exactly.
Slackers.
School is unimportant.
Yeah, look at
Are you
Raheem.
kidding
Whoa.
me? They're skipping school.
Look at Raheem.
All you need is
smile,
math.
smile over there. Just look at
You
him.
don't look very sick to me.
Yes, honest is he.
I know. Wait a second, Isabel. I'm pretty sure you did that once, didn't you?
Oh, shots fired.
Yeah, I know that.
No.
No, absolutely not. Absolutely not. Okay, wait. I have to move this because Jack, you're not sitting close. You need to move closer to.
Yeah, Jack is purposely sitting like a seat over from me, and I'm like really, really offended.
Nobody likes Alex.
Alex is taking it very personally.
Well,
you have
I would
1
too,
over 2.
frankly.
I don't think Jack's been in the camera one day this entire year. Like he's never been in frame.
You know,
Jack.
Look, are you happy?
Thanks, Charles.
We
Are
didn't
you
even
happy
know
now,
he was
Charles?
lost to like the third week.
Was that? Now, let's see. I am ready to talk about this problem, and I hope some of you are ready to talk about this problem.
I think I am.
You think you are?
Oh, I regret saying that.
He regrets saying it. You know, no, Rien de Rien. Do you know that song? Do you know who Edith Piaf is?
Nope.
Yeah, he does. But
Yes, and that's
Right.
not the Inception song. That's La Vie en Rose.
Okay.
that's the only song I really know,
But it's by
understand of hers.
Edith
in French.
Piaf.
Same person.
Okay,
Yeah.
we're gonna start today with Max Allen. Max Allen.
Hi,
starting
Mr.
with
Spraggins. How was your weekend?
How are you?
Oh my god.
I was just telling Sam that you're a closet goth. Isn't that true?
How did you know?
Well, because as I said, I've read your Twilight fan fiction. And
Yeah.
okay, Max, get us started on this problem. What do you do to do this problem?
Okay, so the first thing I did was compute the gradient at that point.
Okay, so what's the gradient, Max?
So at that point, I got the gradient was 3 halves, comma 2.
Okay, and Isabel, did you get the same gradient?
For the gradient, I got, well, yeah.
At the point 3.2.
Yeah, I got 3.
Yeah?
3, yeah, I did.
Okay, there we go. Thank you, Max, for getting us started. Okay, let's see. Jasper, what next?
Well, so then the gradient is the dot product. I mean, the directional derivative is the dot product of the gradient and the direction vector that was the unit vector.
Yeah. Mm-hmm.
So then I checked to see whether those are both unit vectors, and it turns
They
out
better be.
Yeah, so it turns out they.
Because it says consider 2 unit vectors.
But that was super.
If they weren't, then I would be very embarrassed.
Okay, so they both are. They are both unit vectors.
Okay.
And then so I took the dot product, and I got for u I got 7 over 2 root 2.
So wait, let's see. I get 3 over 2 root 2 plus 2 over 2 root 2. Which, how is that 7 over 2 root 2?
I got 7 too.
Oh, wait, I did it wrong. My bad. It is 7 over 2 root 2. Okay, there we go.
And then for v I got the 3/4 minus root 3.
Minus root 3. Okay, Charles Dawson, what do those numbers tell me?
Oh.
Oh, they tell you if you were to move in the direction of u or v, that's the rate of change or the slope of the tangent line along in that direction specifically.
And so one of them is positive. The one in direction of u is positive. What does that mean, Charles?
That means if you were like kind of on a mountain where the shape of the mountain was described by the surface, and you were to walk in the direction of u, you'd have to climb up.
Okay, and that's how steep you'd have to climb up. And steep, you'd have to climb up in a way. And what about the one that's negative, Charles?
That means you'd be going down if you traveled in the direction of v.
So the directional derivative is a dot product of the gradient and a unit vector. So let's say you started off with a non-unit vector. What would you have to do first, Samya? Really?
If you sorry, our mic was off.
That's okay.
If you start with something that's not a unit vector, then you divide by the length so that you.
Right. So you have to make it a unit vector. You have to norm it to a unit vector. And then you just do the dot product. Okay? So let's see. Wait, Isabel, go back. Isabel, you had a question that you sent me via email, which I ignored because I thought we'd answer it in class. Isabel, ask your question about directional derivatives.
Yeah, thanks. Well, I figured it out now. But my question was that it said in the video that, I have like the exact quote, that the direction or the negative gradient gives the direction of minimum increase. And so at first I was confused if that meant like the flattest ascent or if that meant the steepest decrease.
Okay, so let's get some clarity on that question. Samuel, can you answer her question?
Can she, is this referring to cases when it's negative?
Yeah, the negative gradient gives the direction of minimum increase.
Yeah, I think that's when it would have to be when it's actually going down.
So it's a funny way of saying it, minimum increase. It's a bizarre, it's a bizarre circumlocution. Jasper, you have some thoughts about that?
Well, yeah, I mean, the way that I think about it is that if you're at some point somewhere, and if the gradient gives you the direction of maximum increase, then whatever the vector is that's going the opposite direction will be going down the slope or down the mountain in a way.
So, but what does that mean in terms of her question?
In terms of minimum increase, well, if the positive gives you the maximum increase, then the vector going the opposite way, which would be negative, but would give you the minimum increase, because minimum increase is the same as max decrease in a way.
Okay, Coleman?
I think it's phrased that way because you could be in a situation where you're never actually going down. Every point goes up, and so it's just the smallest slope, the one closest to zero. But yeah, it could be either one.
Okay. Jack Schneider, you had something to say?
No, Jasper covered it.
Okay, Julius.
Well, I just think I actually ended up being more confused about this. So, negatively. So it's like if you had your gradient, whatever, and it's going positive, and that's like your max increase. And then so if it were negative, then it just like flipped in the other direction.
Alex?
I'm just confused with so I get that you have the negative gradient, but is it giving you the maximum decrease because that takes into account the magnitude of the gradient, or is it just giving you the direction of the minimum increase, the small if you use the example Coleman set up, where say you're at the bottom of a valley and you can't go anywhere but up, what is the place where you go up by the smallest amount?
Well, so that's a good question. I don't know that mathematically you would have a negative gradient.
Right, so I just wonder whether the negative gradient gives us a direction, or we take it.
Does not the gradient doesn't give you. Okay, well let me ask you all that. Eric, what do you think?
In terms of what Alex just said, or in general? So I'm kind of confused with what Alex is saying. Is she saying that if you took the gradient and you made it negative, then it'd just be pointing in the opposite direction, and if you took the magnitude, it would also be positive because you'd be squaring it and taking.
I mean, well, okay, so what I'm confused about is
it would be the same, wouldn't it?
I'm just confused as to whether we're using this negative gradient to give us a direction or to give us a direction in magnitude, because it's saying that the negative gradient gives us the direction of minimum increase, which intuitively doesn't make sense to me, because when you think of some gradient and then you just flip it, if you're at the bottom of a valley, in Coleman's example, then you're just going into nothingness. So I'm just very confused.
Yeah.
About
so that's a question. I actually have never even considered that kind of question. So the gradient, first of all, the magnitude of the gradient, I don't think is a useful concept.
Yeah.
Just personally, I don't think it's a useful concept. But let's just clarify one thing. And Alex Powell, maybe you can help me out.
It seems very
so Alex Powell, like when I'm talking about the gradient, like I have made this big deal about the gradient is the direction of maximum, it's like steepest ascent, right? That is the direction that the gradient gives us. So how would you respond to, like physically, how would you respond to Alex Johnson's question?
What's Alex Johnson's question again?
So hers is like, I mean, I was saying, so what does it mean to say minimum increase is, I think, part of the question. I mean, do you have any thoughts about that?
Well, it's like kind of like what Jasper said. I think it's, the minimum increase is basically like the maximum decrease, since it would be the negative of the gradient. So you'd be going back down that steepest part.
Yeah, and I don't exactly, Isabel, to your point, I don't know what prompted me to use that language, except that maybe that's what I was thinking at the moment. The question that you asked, though, is if you were at a minimum point of the, function, I don't know the answer to your question. It's a really interesting one, but I don't know the answer to the question, because I don't know that there is no way in which you could have minimum decreases if you're at one of those optimal points. We will talk about optimization after the break, and maybe we can figure it out then. Yeah.
And you've been saying the gradient is the steepest ascent. So that means
the negative gradient is therefore the steepest descent.
But so in terms of the gradient first, it's just that it's always going to be it's not always positive.
No, it may be negative. It may be positive and negative, but that you still might be going in the steepest way.
So it's like the steepest. It's not. You're not necessarily
vector,
going up.
Right.
Though.
It's a vector.
It's just like the steepest.
Right. You could be going across the thing.
Okay.
Yeah. You could be going across the contour that was. So your function might be a complicated function, and the vector, right, for it to be positive. Let's say it's a positive x value and a negative y value. That means that this way is the steepest descent. Make sense? Actually, I should say this way is the steepest descent.
Yeah, that makes more sense.
Okay, Isabel.
To Alex's question, I was thinking about that a lot over the weekend. Like, what if it's at a local minimum or maximum? How does that work? And then I was thinking maybe the gradient doesn't exist at a local.
Yeah, that's what I'm wondering
minimum.
too.
Like, it's a point, right? It's not like a contour.
I think it would be a zero vector.
Like it might be a zero vector.
Yeah, and that's what I'm wondering about. We will talk about how you determine if there's a local minimum. And I think that probably you're right, Isabel, that it has to do with the way the gradient looks. The way that we'll do it involves partial derivatives, but those partial derivatives are also obviously important in the gradient, right? Because the gradient is partial derivatives. So I don't know the answer to your question right away, but it is an interesting one. Let us continue, because I want to talk about a couple of other things. This is an easy type problem, but this would be, I think, a good exam problem. And so I want to talk about how a person might compute this. Logan, help me start with this. What would I do first?
Okay, so first you would take the partial derivatives with respect to x and y.
And that would give me the...
And then you end up multiplying those by I and j respectively to get the...
Wait. So for A, I'm talking about A. So first I take the gradient. That's the gradient, right? Your partial, it's a vector that's the partial with respect to x, comma, the partial with respect to y.
Correct?
Okay, Akshay, what would I do next?
For part A?
Yeah.
Well, you would want to plug in the 3 and the -1, respectively.
And what would you get out? What kind of a creature would you get out? Would you get out a scalar or a vector?
Vector.
Okay, cool. Then what, Akshay? Then for B, so we've done A.
How was the gradient?
Yeah, the gradient.
I'm not exactly sure what that notation is.
Okay, so what does that notation mean, Sam?
But it's the gradient.
This notation here. I think Akshay is confused about this notation here.
Oh, he's the directional derivative.
Yeah, that's the direction of derivative in the direction of u. Okay, Raheem. So we found the directional the gradient at 3, -1. So how do we find that thing by the arrow?
Now you just do the dot product of the gradient with the unit vector.
Right. As long as this is a unit vector, we're in good shape. Okay. And then, so for this one below, it's A again. How interesting. So Samya, what would I have to do for this one? How would I do it differently than the first one?
Well, it's essentially the same thing, but I don't think that this vector is a unit vector. So first you have to. Wait, it's not, right?
It's definitely not.
Okay,
right?
well,
it's linked.
I know it's not a unit
vector. It's not a unit vector. Right, so you have to make it a unit vector. So that's, when I first talked about unit vectors, and when I always talk about them, one of the things I often say is that unit vectors are pure direction, which is why we like them. This is an example of a moment when we only care about the direction of motion. So that's why we need a unit vector there. So go ahead, Samya. So you make it a unit vector. And then what?
And then you basically do the same thing where you already have the gradient. And then you do the cross product. I mean, sorry, not the cross product. The dot product of that gradient with that unit vector.
Fabulous. Great. Okay, so that's like a more complicated problem, but it's only more complicated because you have to make a unit vector. Okay. Let's see here. Jasper, yes, you have a question?
I actually have a question.
Sorry.
Because I remember in the video you did with cosine theta and sine theta, as opposed to doing, just dividing by 5, or dividing by. Is it? Right.
It's interesting. And I don't know if I don't remember if I derived where that comes from.
Well, yeah, you did with
okay.
the triangle. But is there a better one? Is there one we should use more frequently? Okay.
No.
Okay.
I would actually probably make this a unit vector. That's how I would do this.
Okay.
But there are other ways to do it. Okay. Again, I want to spend more time today talking about making sure we're algorithmically solid. So Charles, would you read this problem aloud for us? Thank you.
Consider the paraboloid z equals f of x comma y equals 4 plus x squared plus 3y squared. If you are located on the paraboloid at the point 2, minus 1/2, 35/4, in which direction should you move in order to ascend on the surface at the maximum rate? What is that rate of change?
Okay, Max, help me out. So what is this problem asking for?
So it's asking for 1, the gradient, and then 2, the magnitude of that gradient.
Okay, good. Eric. So Eric, tell me what to do.
So first I would take the gradient of.
Okay, so let's see if I can get the gradient. I'm going to take the gradient of z. Okay, don't tell me, Eric. Don't tell me. Don't tell me. I got a gradient.
Eric, don't tell him.
Thank you. I got a gradient. Now I'm ready. Now tell me what the gradient is.
I got 2x, 6y.
That's what I got. I feel so validated. Logan, what next?
Thinking about this, I'm thinking. Well, you would plug in the points, but I'm wondering where z comes into this, because you're not going to have that in your gradient. Well, no, you should.
I don't think it.
Yeah, I was wondering about this.
Yeah.
I don't think it matters. Yeah, it's just a point in space. It's just the z. Sure. It's just that is the z value. So let's see. I'm going to follow your teachings, and I get a vector. What is the vector that you got, Logan?
4, -3.
4, -3. Oops, I got the wrong vector. But you're right. 4, -3. Thank you. Okay, Coleman. Now what do I do? So I've answered one of the problems. What's the problem I've answered? Yeah, Coleman.
Oh, sorry, I was muted. You've answered which direction you move in, and so you're going to need to find the magnitude of 4, -3.
To find the rate of change. So wait, to your point earlier, right? So 4, -3. If I'm moving 4, -3, so I'm moving like this. Yes. That is the steepest ascent on the surface, whatever that thing looks like.
Okay.
And then Coleman is saying to find. So then I want to find the rate of change. Hey, Samya. I want you to stop your JV behavior on the last thing. Tell me what the magnitude of that vector is. I'm gonna cry if you can't tell me instantly.
Called you JV.
5.
You said that with such conviction.
That's what I said.
Yes.
I said 5. Okay.
5.
That's how I answer everything.
Yes.
Classic choice.
It's like 3, 4, 5. I mean, it's one of those kind of famous triples. Have you ever heard of 5, 12? What's the other one? 5, 12.
13.
Yes, there you go. 5, 12, 13.
Yes, Julius.
Okay, good. Okay, Raheem, would you read the next one?
We have a problem.
Oh, what's your problem?
Well, this could be addressed now or after this problem, but I'm wondering, will we need to know how to, like in one of the videos you showed us how to do, like, make an equation for the generic path of either greatest or least.
I think we're going to talk about that in a second.
Okay, cool.
I think we're going to talk about that today.
I have a question about the one we were just doing.
Yeah.
Well, it's kind of basic, but so we find that our rate of change is 5, but do we like is there like a unit or something? I feel like that's like a weird way to just leave it like that. Okay,
it depends on what your units are if you're particle moving and stuff like that, but don't worry about it. Okay, anyway, Raheem, would you read the second question?
Yeah. So if you are located at the point 2, negative 1/2, 35 fourths, in which direction should you descend on the surface at the maximum rate? What is the rate of change?
Okay, Alex Johnson, that's easy.
So you just take the negative gradient, so it's going to be negative 4, 3.
Negative 4, 3.
And the rate of change is...
So let's see, negative 4, 3 would look like this, right? So it's my point, though, is that way.
Yes.
So same vector, different direction, opposite direction.
I just feel like if the y is up, then it's ascending, and if the y is down, then it's descending. So I feel like the first one was ascending. I know, but that's like how my brain always.
Well, I'm about to cry as hard as I was. Hey, Samya, what's the rate of change?
5.
No, it's not. It's negative 5.
Oh, is it?
Isn't it?
How can the square root of something be negative? Oh, wait.
No, because you have the negative magnitude.
This is why don't say things with certainty.
When I think of the rate of change as being like speed here, so I would think it's a speed question, not a velocity kind of question. So I would say
Would you accept both answers on the exam?
Oh my God, who knows? For you, Alex, never. Okay. Here's an interesting question. Okay, at the point 3, 1, 16, in what direction is there no change in the function values? Let's see, Max, what do you think you should think about here?
So if our gradient is 2x 6y, then at the point 3, 1, in what direction? Okay, so at the point 3, 1, the gradient is 6, 6, right?
And so then I'm thinking about in what direction is there no change in the function values? So,
So I want to take when I dot, or I take the dot product of 6, 6 and some unit vector, I want to get 0, I believe, right? So,
when you take the magnitude, you mean?
No, when I take the dot product, right? So I think maybe in the direction...
Oh, yeah.
1 over
there
root...
might be multiple directions.
Yeah,
What was
I think at least one could be 1 over root 2 and then negative 1 over root 2.
That was mine.
Yeah, that would work. I can think of. I mean, yeah. I think there might be more. What other one?
One common negative one.
One common negative one. Okay, that's a unit, not a big unit vector. But it's true that in one common negative one. Okay. Yeah. That's actually the same one he said. It's
now I realize that. Yeah.
2x comma 6y. So you plug in the point.
Isabel,
so this is our gradient.
No, I'm working on it.
Question, Mr. Charles?
Oh, wow. Yeah, Logan.
If this is the question, like in what direction, parentheses, like S plural, I guess, would you want us to give a generic expression for concentration, or would you want us to give an example?
Too. But it needs
I can't hear you because Isabel is talking.
Yeah, if you want it to be.
Sorry.
Isabel, can you stop talking so I can hear Logan's question? Thanks.
So, given like the way this question's set up, like in what direction, parentheses S, like plural, should we give an example or should we give a generic expression?
It would be awesome if we could come up with a generic. So I would probably say capital D U of F of 3, 1 equals 0. Because that tells me there are infinitely many unit vectors from that point that are, in any of those directions you would not be moving at all. So Alex, that brings me back to the question we were talking about earlier, it's an interesting thing. Okay, we need to move forward.
Wait, Mr. Spraggins?
Okay, this is what
Spraggins,
yes,
wait.
Charles.
There wouldn't be infinitely many unit vectors, would there?
No, I don't know, but I suspect there would be. I don't know why not.
I guess it depends on the case. Because if you have like just a bell.
So they're all of the form A over. They're all. Like in Jasper's example, they're all of the form A, negative A, or negative AA, right? And so then if I figure out the unit, maybe they're all of the form. Maybe there's only one. I don't know.
But to be unit vectors, there are infinitely many vectors, but there are only 2 unit vectors.
Well, so I guess there's 1 over root 2 and negative 1 over root 2, and then negative 1 over root 2, comma 1 over root 2.
Is that it?
I think that's
there
right.
are infinitely.
No,
infinitely many unit
Charles,
vectors.
Yeah, because you can just
infinitely
divide.
many unit vectors. That's not unit. You just keep dividing.
Yeah. Because if you multiply it or whatever, it's not a unit vector anymore.
Right.
No,
So I
I
guess
mean,
you're
like,
right, Charles.
No,
I think
because
you're right.
They have to have the same value. You can have like 3/5 and negative 4/5.
Well, that's not the same direction.
No, that's what
But that wouldn't
you
work.
can't just like take any unit vector.
Yeah.
Right?
Yeah, because 3/5 and negative 4/5 would not make that 0.
Right.
Yeah,
Like
okay.
anything is just it's an equilateral right triangle.
Yeah,
So anything is
okay.
gonna reduce.
We need to talk about this next topic just because I think it's an important one. Okay, consider the upper sheet of a hyperboloid of 2 sheets. Okay, it's that function there. And it says, verify that the gradient is orthogonal to the corresponding level curve at that point. This is so hard. I have no idea how to do this.
No,
I'm so confused.
There's a condition.
So, Isabel, you have an idea.
well, the gradient. Sorry, I don't know if this is helpful, but the gradient has to be orthogonal to the contour line. That's like.
Yeah.
I don't know if
That's
that's
a
in
fact,
the
but
definition.
I'm trying to prove that fact.
So.
Yeah, go ahead.
Well, I mean, the gradient shows the maximum rate of increase, and it would make sense that it would have to be perpendicular to, like, if you continue along this line, you'll get all the points of the same value, so then the furthest away from that would be 90 degrees away.
Okay, so I think you're thinking geometrically, which I like. However, I think this is a computational problem. I think this is a very computational problem. So, I mean, I don't know. I always look at these problems, and one of the things I often think about is if I encountered this on a test or exam, what is one thing I know I have to do? Akshay, what's one thing I know I have to do?
Well, take the partial derivatives.
Yeah, so actually let's all compute the gradient at 1, 1, which is actually in this case not super easy to do. It's not that bad? Can you say it's not that bad?
I'm not sure if I'm taking these derivatives properly.
Yeah, I know. I mean, that's why I want to do this.
Is the entire exam going to be calculator?
Uh-huh.
Awesome.
So at 1, 1, I'm getting... Okay, I got it. So Akshay, can you help me see if I got the right answer? Because I'm very needy.
1, 2. All right. For the I component, I got 1.
Yeah, me too.
And J component, I'm gonna get 1/2.
That's what I got. I feel much better. Thank you. I have been.
How do you get
1, 1/2?
I get
How do you get
2,
1 and 1/2?
Oh, nice.
Okay, so Alex Powell, why don't you let me read you my derivative? See if you like my derivative, Alex Powell. My gradient. So I got 4x divided by 2 times the square root of all that stuff.
What?
That's my I component of my gradient.
Oh, to the negative 1/2.
I forgot.
Comma.
Right. I got that.
2y over 2 times the square root of that stuff. So that was my gradient.
Oh, I was plugging in the wrong point. Never mind.
Okay, there you go. Okay, so we still haven't, so we found the gradient at that point. Now I want to find that it's orthogonal to the level curve at that point. Max, help me out.
Okay, so the level curve, first, I think we want to find what level it's at, right?
Okay, yeah, I'm cool with that, yeah.
So f of 1 comma 1 will be the square root of 4, which is 2, which is very nice. So then we have 2, the level curve would be 2 equals root 1 plus 2x squared plus y squared, right?
I agree, yeah.
So then we could square both sides and subtract 1, which would be 3 equals 2x squared plus y squared. And then and then that's like a is that an ellipse?
I think it's an ellipse.
Yeah, is that an ellipse?
Yeah.
Yeah.
And then we want to okay.
You can pass if you want to, Max.
Okay. How about, can I call on somebody?
Yeah.
Okay, Eric.
Haha. So we got some good work there, though. We found the level curve, right? And it's an ellipse. Okay, we're good.
So I think you could find. So could you find the unit tangent vector? So you could take the dot product and prove that.
Interesting. How can you do that?
Well, I would solve for
geniuses.
Y, and I would take the derivative of that. Oh wait, that has to be a vector valued function. Oh, so you make the ellipse a vector valued function, and then do that.
Wow,
So-
This not sounds like a lot of work.
Wow, that does sound like a lot of work.
Yeah, I don't know.
I don't know.
Lazy police vectors.
Okay, so Max, how do you like that idea?
I like it.
How are you?
Else has an easier idea.
How are you going to enact that idea, Max?
Well, hold on. Let me think for a second.
Uh-oh, you have someone else. Coleman has an idea.
Okay, Coleman.
Could you find a radius of the ellipse and prove that the radius is orthogonal to the gradient?
It's an interesting idea, except I'm not exactly sure what a radius of an ellipse is. So do you mean the minor axis, major axis? Which one would you find?
Any of them.
That's a lot of work.
Okay, so either the major axis or the minor axis. Okay, interesting idea. I guess Charles has an idea.
So I think you can rearrange this into the standard equation of an ellipse from which you would be able to find the length of the major and minor axis, and then you can easily parameterize it. But then you can parameterize it easily into something with with cosine and sine t, and then you could use Eric's
so
idea.
you have to remember how to do that, of course. Ooh, you look sad. So ellipses are like A cosine t, B sine t. Those are ellipses typically. You look sad, Jasper.
Yeah, that's
yeah.
Excel elementary functions.
One of my actually saddest moment ever on a math test. I had two really sad moments on a math test. One of them was on only two. But one of them was well, I had much easier math teachers than you do.
Yay.
So, but one of them was having to parameterize ellipse on some. I was like, I don't remember how to do that. But anyway, but now I know. Okay. Wait, Logan, you had an idea.
Something that I'm thinking about is that you should technically have no z rate of change if you're going like across that contour line. So is that helpful information? Like that could give us a I don't know. I don't know. I kind of lost my mind, or like lost my train of thought. But
you lost your mind. That's intense.
But isn't that like helpful information?
I don't know. Alex, wait. Let's say Alex has an idea.
So this is like not really, I don't know how helpful this is, but I was kind of thinking something like tangentially similar in that all level curves are parallel to the xy plane, correct?
True.
So I was thinking like, okay, if they're all parallel to the xy plane, we should just be able to prove that like it's parallel to something that's parallel to the xy plane, or perpendicular to the xy plane, and therefore it would be orthogonal to that level curve. But obviously you can't just pick like any random vector that lies along the xy plane, and I was wondering why not, if they're all parallel.
Oh, because the gradient at that point would not be orthogonal.
Oh, right.
You know, it's at a point. I mean, actually, I think I like the one that is most appealing. The idea I've heard that's most appealing to me is to parameterize the ellipse. And that came, I think, from Coleman and Charles. So wait, do you have an idea?
Well, it's not necessarily okay. So I was thinking that sort of like we did in the last one. So we know that if we take the dot product of the vector that we found, the gradient, and whatever vector that we kind of want to get out of the ellipse at some point, then that has to equal 0 because we want them to be orthogonal. So can we like set up some like an ideal like something general for that vector that we're looking for, and then prove that that's on the ellipse as opposed to finding out the ellipse?
So one of the questions to me is, what does it mean to find a vector on the ellipse? Because all vectors are straight things. So any vector that you find is not, I mean, all of them are linear things, right? So there's no curvy vector. What I think some people were talking about was this idea of doing a vector-valued function, which, do you remember how those things are created? Yeah. Isabel.
Oh, that makes sense, yeah.
What if you found the equation of the line tangent to the ellipse at that point, and then did the opposite reciprocal slope, and then write an equation for the line of the gradient?
Well, I think one of the things, that's what 2 asks, it says, can you find the equation of a line tangent to a level curve? But the question is, for that, Isabel, is how do you even do that?
Well, can't you just solve, I mean, we know how to find dy dx using implicit differentiation for this ellipse, and then we know that that would be the slope of the tangent line, and then we have a point. So
you could write the equation of a line tangent using implicit differentiation, but that would give you only information about dy dx. So.
But I just mean, if that line is tangent to the ellipse at that point, then a line normal to the ellipse at that point would just have the opposite reciprocal slope as that, and so then we could compare that to the gradient to see if they were the same thing.
I like the idea, okay, and so my nervousness is that, and I think it will work, Isabel, but I just haven't tried this kind of method to solve this problem, so I think it will work, but I see people working on this. It's interesting. Charles, what are you doing?
So I'm just following through on the parameterizing it and then taking R prime and getting the dot product of that to see where it leads.
Yeah. Okay, so this I'm going to cut this conversation off right now. I think that actually Isabel's method will work. Another method is to use the parameterization of the ellipse. Yes, we should. Yeah, that's something I would hope we would know. Jasper did make. Can I show everyone? Jasper did spend a lot of time making a beautifully typed.
Yeah, I typed it all up.
You know, Isabel, that's why I like you, because you typed it all up. These are beautiful equations.
Yeah, they were really hard.
Intense. Okay. I need to move forward to this fact just to make sure. Obviously, the gradient in 3 dimensions, it's not hard to figure out what it would be, right? It would just be the partial with respect to x, comma, the partial with respect to y, the partial with respect to z, and then your directional derivative would just be, you'd have to have a 3 dimension.
Why do I not see that?
Well, so if you have w equals f of x, y, z, so you have 3 variables, perhaps I should say. Okay, so it's easy to extend this to however many dimensions you want to. And as I said later, the gradient is one of the fundamental ideas of multiple variable calculus. We'll encounter it over and over and over throughout the year. I want to make sure that we get this, that I spend this time talking about the exam, because this is our last time before we meet before the exam. So here is a list of topics for the exam. So I want to make sure that I have said these things and you've heard it. Huh? What? You have a question?
I don't think so this time.
Okay. Jack, would you read these?
Surfaces in 3D space, Cartesian coordinates in 3D space, 3D coordinate system, distance formula.
Wait a second. Distance formula. There are multiple distance formula in 3 dimensions, right? Mm-hmm. There's a distance formula like between 2 points, but there are also distance formulae between planes and things like that. Yeah, I think that's fair game. I mean, I don't know if it's a great question to ask on the exam, but it's fair game. So distance formula. Go ahead, Jack.
Functions of 2 or more variables, domain, range, level curves, contour diagrams, planes, domain, limits. You say domain twice. Limits and
what can I say? I'm sorry. Gosh, Jack, you make me feel like a crud. He's mocked me. Okay, this is actually, remember, this is a big emphasis on this test because you haven't really been tested on this before. So I promise you there will be a number of questions about functions, domain, range, etc., etc., etc. Okay, let's continue. Akshay, would you read these for us?
Vectors, geometry of vectors, components of vectors, unit vectors, magnitude of a vector. Dot product.
I assume everyone knows that. Okay, go ahead.
Geometric and algebraic definition, using dot product to find angles and determine perpendicularity. The equation of a plane with given normal vector passing through a given point.
That's kind of a classic multivariable calculus question. I remember when I was studying for a single variable calculus test many years ago, the parent of a friend of mine was like, definitely study how to write the tangent line. And I was like, really? Why? And she was like, well, just definitely study it. I mean, that's one of those kinds of questions that I almost feel obligated to ask on the exam because it's such a classic use of multivariable calculus. Say again?
How to write a tangent line?
Yeah, well, this one here is writing the equation of a plane. Okay, go ahead, Akshay.
Cross product, geometric and algebraic definition, volume, equation of a plane using 3 points.
Yeah. Okay, so you will be able to use your calculator on the whole exam, so I'm not expecting you to do anything by hand, but, you should know what the cross product is about. Okay, let's see. Sam.
Definition of a vector value function, how they are drawn, limits, continuity, differentiation, integration, velocity.
Okay, so that's like why we need them. This is kind of easy stuff. Yeah.
Velocity, acceleration, and speed.
Yeah.
Differential geometry, unit tangent vector, principal unit normal vector, tangential and normal components of acceleration, arc length, curvature.
Yeah, and I mean, if I'm going to ask a curvature question, it will be something probably about the circle. I mean, what are they called? Osculating circle. Remember those? The things that you need. Remember on the test I provided, on the test on curvature, I provided some formulas. I don't know that I'm going to provide any formulas. In other words, I'm not going to ask you stuff that's crazy, cuckoo, hard to remember, I don't think. But I'm not going to provide any formulas. So any formulas that you need, I absolve myself of those right now. But I mean, I would not spend a lot of time memorizing 16 different formulas for curvature. I would know what curvature means, maybe how to find it, given a circle, that sort of stuff. And you can ask me questions about that in a second if you want to. We need to get through this. Raheem.
Yeah.
Differential equations. Definitions. What a differential equation is. How to tell if a given function is a solution. What an IVP is.
It's an initial value problem, right?
Yeah. Numerical solutions to differential equations. Euler's method, slope fields. And analytical solutions to differential equations. Separation of variables, linear first-order equations, homogeneous equations, and Bernoulli equations.
Now, in the whole scheme of things, right, this was a small unit of what we've done this year, so don't spend lots of times being like, wait a second, I want to spend hours learning how to do homogeneous equations. You know what? Cut your losses. Yeah, Charles.
One of the videos was like the final method of solving DEs.
Not here, so it's not won't be on the final.
Okay.
Okay. Great question. And honestly, what am I most likely to ask about in terms of differential equations? The ones that are most useful. Yeah. So I'm probably gonna ask the most typical things. Okay.
Wait,
now this I want to spend.
Sorry.
So that there's another kind of substitution method where you use like u equals x plus 7y plus something. It's hard. So come on, who has time to do that on the exam? Okay, here's what I really want to emphasize on the exam, though, and let's talk about this in a granular detail. So, Samya, would you read the first thing there?
Partial derivatives, qualitative understanding, visualizing.
Stop. What do I mean by qualitative understanding of partial derivatives? Yeah?
Well, I picture that as sort of like you have like a graph and you're able to like represent what it means.
Yeah, so it's not like computing partial derivatives, it's what do they mean physically, okay? So I may ask you questions about partial derivatives like, here's a function and if its partial derivative is negative, what does that mean, okay? Go ahead, Samya.
Visualizing on a graph, estimating from contour diagram or table, computing mixed partials.
Okay, so the only part that's algorithmic there, is computing partial derivatives and finding the mixed partials, right? Everything else there is qualitative, like estimating, looking at data and estimating partial derivatives. Okay, so there will definitely be questions about partial derivatives, many of them. Okay, local linearity. You know what? Forget that. I don't think there are any questions on that on the exam, but anyway, let's leave that as a later question. I should have gotten rid of that. Directional derivatives. Jasper, what am I talking about there?
Oh, directional derivatives is the rate of change going in a certain direction from a point in 3D space.
Yeah. Okay, the gradient. Alex Powell, read those for us.
For gradient definition, geometric properties, relation to directional derivative, relation to contour diagrams, and surfaces.
Okay, and let's see. So when I talk about geometric properties, Alex Powell, what am I talking about there?
Kind of like that, like the maximum increase, or the negative gradient has the minimum increase kind of thing.
And relation to directional derivative, I'm just trying to make sure that you know that the gradient is part of that expression. And then, Jack, what do I mean by relation to contour diagrams and surfaces?
They're perpendicular.
Yeah, orthogonal. They are perpendicular to the gradient is perpendicular to the contour lines. Okay, the chain rule. What do I mean by that, Coleman?
Applying the chain rule to when you're taking the derivative of something and with multiple variables.
Yeah. And so remember, there's that tree diagram thing, and you have to multiply all that stuff, so it can be ugly looking. But that's what I mean by the chain rule. It's a chain rule in multivariable things. And last but not least, Taylor approximations. Logan, what am I talking about there?
I was hoping you wouldn't call on me because it's the only thing that I haven't looked at yet, so I don't remember.
Oh, liar, pants on fire.
Sorry.
Okay, Isabel, go for it.
Taylor approximations. So what happens is if you have like you have a differential equation and you want to approximate a solution to it using a polynomial. So if it's first degree, you'll get f of xy equals f of 0, 0 plus the partial derivative with respect to x times
so it's using
like
a formula.
at
Wait,
0,
back
0.
up, Isabel. It's not. We're not talking about solutions to differential equations here. We're talking about approximations to functions, to multivariate functions. So, for example, if I wanted to find a polynomial expression for, I don't know, e to the xy, right? That's a multivariable expression. And the way it's actually not that bad, not that hard to remember. So you have to take the partial with respect to x times what, Jasper?
Well, partial with respect to x times x.
Okay, and then the partial with respect to y times y, and then you have to have the function value at the point, and then you have to have, if that's for the linear approximation, but for the quadratic approximation, you have to have the partial with respect to x twice times
xx, and then x squared over 2.
x squared over 2, and then the partial with respect to y times y squared over 2, and then partial of xy times xy. So, I mean, it's actually not too bad to remember. I don't have it memorized at all. I just remember that, the partial with respect to x has to be multiplied by the linear term in x. Partial with respect to y has to be multiplied by the linear with respect to y. Okay, that is all the topics on the exam. Okay, I want to talk to you about a couple of things about my philosophy of exams, and just in general, so that we're all clear on it. I actually think the exam should be interesting, should have some problems that maybe teach you some use of this that you haven't learned before. But I also don't think it should be trivia seeking. So I don't feel like you should, like when I say, do you remember those crazy expressions for like normal acceleration and stuff like that? You know what? If you had to do that for a living, you'd know those. And if you had to do them on a test, you could look them up, or I would give you the formulas. There's not a lot of point for me to have you do that. It's like that. It's like what you were talking about, the substitution method for the differential equations. That to me is tough to, justify putting on an exam because, it's like trivia almost.
Like UDX thing, UDX VDU.
Yeah, I mean, so that's just tough to do. Oh. So I want you to focus on big ideas. Okay, so that's the main thing. You might see things that are like, that's a novel way that we haven't really talked about it, but I see that as part of my job in creating a fun-filled exam. Second, you should expect the exam to be a solid, packed 2 hours if you took it in 2 hours. Like it would be a packed 2 hours, and you would have to be working as fast as you could. Now, I think you can take up to 3 hours on the exam. I don't know what you're going to do. I'm going to tell your proctors that you have up to 3 hours on the exam, but you can complete it in 2 hours if you are like racing through the exam. That's not my goal, but you could do it if you were like, I only have 2 hours to spend on this exam. You could do it. So, but if you took it in 2 hours, it would be like you were working every minute as hard as you could for 2 hours. Okay, I think so. That's something. It's meant to be really. You could finish it in 2 hours, but it would be like you could not spend a lot of time being like, now wait a second, what's that formula? No, you would have to know it right away. I actually graded your problem sets, so you'll get those back today. They were pretty good. They were very good. Who has questions about the exam that I can answer right now? Yes, Isabel.
Did you say that there won't be tangential and normal components of acceleration on it? Is that, sorry?
I don't. Here's the funny thing. I don't actually remember right this moment, but that seems to me like pretty trivial stuff that, I'm not asking you to memorize those crazy formulas, and it would be hard to do that. So, okay? Jasper.
Well, I'm kind of in the same vein as well. I'm just really kind of trying to figure out what I should be memorizing tonight, really. To prepare for the exam. And so, in terms of curvature, in terms of tangential and normal, and also, there are
17 different forms for curvature. Yeah. So, think about the ones. Think about one that's. Okay. Think about the ones that are most useful and that we use most in this class. You could memorize a whole bunch of them, but I'm not gonna.
Well, and
So
also,
we should
so you
memorize
mentioned the distance formula from a plane to a point.
Yeah, I think that you should know the distance from a plane to a point. Sonia.
Could we possibly have some of the answers to the review problems?
I personally have not made answer sheets, but I'd be happy to provide an answer if you have a specific question you're concerned about. I just don't have answer sheets for them. So, okay. And I don't think I have time between my students have to take this exam tomorrow. So I don't know that I know I do not have time to create all the answers for tomorrow, but I'd be happy to answer any question you're having problems with. Okay. So I apologize. It's just that that's not my MO typically. Coleman, yes.
Where are these slideshows stored, if they are at all?
They're on the website under week 1 or something like that. It has the slideshows.
Okay, and so it'll also have.
And those have been updated recently.
Okay, and so it'll also have somewhere all those curvature equations?
So there's a sheet in the week on, what's it called, on differential geometry that says, here's a list of all the equations that are of differential geometry.
I think it's like week 7 or 8 or something.
Yeah, I can't remember and I'll make sure that the slides are updated if they're not. I don't remember if I turned them on, but I have all the slides. So all the slideshows should be there. They may not be there right this moment, but they will be. Alex Johnson, quick.
So if we have 2 hours is the very, very minimum, and we have up to 3 hours, what time do you think, what time are you estimating that people will generally finish?
I have no idea. Okay. I mean, I think some of the problems are quite easy, but some of the problems are not quite easy. And part of the deal with an exam that's hard, especially in the material of this class, there's so many things I could ask. So that's what's hard about it. Is there's a lot of options, aren't there? I could ask you there's all sorts of things we learned about the cross product. I could say prove something with a cross product. So I don't know. Some of the stuff I think you'll find laughably easy, and some of it I hope is a little harder. It is in color. How's that work for you?
Okay.
So there's some color on it. And there's some choice. You get to choose some problems.
Oh,
yeah. So there's some choice in the exam. I actually sometimes think that's not a good thing. Because,
it makes me
you'd be like, which one do I choose? Okay, I have to go. Y'all are awesome. Have a great break. Rest a lot. Be amazing. Don't think about math. And I'll see you all next in January of 2015, the year many of you graduate from high school. Okay, bye. Hope you do. Let me know if you have any questions before you take your exam.
Thank you, Mr.
Bye.
You scrub. Why did you guys skip school?
Guys. When are you taking your exam?
We take it Friday.
That's so unfair.
No, it's because that's the only time that our proctor dude can proctor it.
Well, I mean, you guys have a teacher at your disposal.
Yeah, because tomorrow.
Yeah, but we don't have 3 days at our disposal.
You know
how much we could do with 3 days?
Tomorrow we don't have school.
That's a whole day of study.
I don't have school today.
And then on Wednesday and Thursday we have other exams.
We have other exams.
Where's this?
Yeah, this sucks.
This is not funny.
Okay, bye. Oh, okay. All right. How do we turn this off?
The plight of the Murrays.